All right, good morning, chemists. We'll get started. Nice to see your shining faces on this rainy day. All right, so we'll just jump right back into electrochemistry, which we introduced last week, where we looked at kind of some review of Chapter 4, Chem 1210 material. So we looked at oxidation states of elements. Basically, if you think charge, where oxygen and hydrogen, if they're in compounds, are most likely -2 and +1 oxidation number. And that allows you to figure out what is the oxidation number of all the other elements, because oxidation numbers must add up to charge. So if you think charge, you'll be right 98% of the time. And then we related this to redox reactions, where redox stands for reduction oxidation, where something is losing its electrons, so oxidation, and at the same time a different substance in that reaction is being reduced, so gaining electrons. We need both of those to occur in a redox reaction. We can't have two things that are oxidized or two things that are reduced. No, one thing has to be oxidized, one thing has to be reduced, where then we tracked how these electrons transfer from one half reaction to another, and balanced these redox reactions. Electrons that are given up in an oxidation reaction funnel into the reduction reaction, where those number of electrons must cancel out with one another. And so we looked at some examples of balancing redox reactions in acidic conditions, where I showed you this demonstration where, yes, we can mix together permanganate and reducing agent, and it may seem like, oh, if I mix these two things, then a redox reaction will occur, but not necessarily. So what I showed you is I mixed these two things and no reaction actually occurred until I added a drop of acid. So that's what I mean when we balance in acidic conditions. And I just realized we didn't actually finish this slide, and then we'll move on to the next section, actually putting numbers into things. So we balance this redox reaction in acidic conditions. To balance the hydrogens, we added H+ to get all of that balanced before balancing electrons. So we can also conduct redox reactions in basic conditions, which actually follows a different reaction. It'll have a different redox reaction, but converting between the two is pretty straightforward. So right now I have the pre-balanced reaction in acidic conditions. We did that in the previous slide. We got that the number of electrons transferred, I think, was 10. And so to balance a redox in basic conditions, if you start with in acidic conditions, simply all we have to do is neutralize that acid with a base. So we want to add 16 equivalences of hydroxide to both sides of this reaction to balance it in basic conditions, and then we just have to clean it up a little bit. So if I mix together 16 equivalences of H+ and 16 equivalences of hydroxide, what will I get? Water, but how many? 16, yes. So these two things, when you add them up, react, and now you have 16 waters, H2O, plus everything else. So 2 permanganates, 5 oxalates, in this case, still gives us 2 manganese 2+, 8 waters, and 10 CO2s, and those 16 hydroxides, because I added hydroxide the same amount to both sides. And so now we can just clean it up, because notice that there's water on both sides. And so simply we just cancel out all 8 of these waters, leaving us 8 on this side. And so we see that the balanced chemical reaction now is 8 waters, 2 permanganates, MnNO4, plus 5 oxalates, gives us 2 manganese 2+, 10 CO2s, and 16 hydroxides. So now this green reaction, it's the same reaction that we inspected earlier, but now it's just balanced in basic conditions. So we see that the stoichiometry of the things that are actually reacting are still there, but this is the reaction that will dominate if hydroxide is mostly present instead of acid like we had previously. And so the strategy here is once you get it in acidic conditions, just add hydroxide to get it back. get it back to basic conditions. All right, and then cancel any excess waters if they appear on both sides. That's typically what happens. There'll be water on both sides, and you just cancel out to the, I guess, least common coefficient. All right, so now we finished that section. I just realized that. So now let's talk about cell voltages. We're still talking about spontaneous redox reactions, but now we're going to harness the work of those electron movements moving in a redox reaction, so they're useful to us. So this is basically how batteries work. It's how this potato demonstration works. So let's look into it. All right, so I have an example of a spontaneous redox reaction. We call this a voltaic cell. Once it's set up into a cell like this where we have the cathode and anode in contact with one another via a salt bridge, we call it a voltaic cell when it's a spontaneous cell. So if we look at this reaction, we know it's spontaneous because if we look at the two reactants, we have zinc solid and copper 2+. If we go back to our activity series here, remember the rule. It's if the metal is higher on the activity series than the cation, then a redox reaction occurs. So that's how we know that this is spontaneous. That's how we know it's a voltaic cell. So if you look, just to confirm that yes, a reaction happens. What are we mixing? Zinc solid and what? Copper 2+. Yep. So we see zinc solid, copper 2+. The metal's higher on the activity series than the cation. So yes, indeed, this is a redox reaction that happens. But now let's go into more detail of the details of this redox reaction. So here's the full balanced redox reaction, but let's get those half reactions. So split it up because we know electrons are being transferred. So sometimes inspecting the half reactions allows us to see more in depth of what's happening behind the scenes, specifically the electrons being transferred. So I'm going to go ahead and just get the oxidation numbers of everything, just so I can tell what is being oxidized and what's being reduced. So zinc solid is 0, copper 2+ is 2+, zinc 2+ is 2+, and copper solid is 0. So you can see zinc is being oxidized because its oxidation number is going up, while copper 2+ is being reduced. So because its oxidation number is going down, it's being reduced. And so we split up these half reactions and balance them individually. So the oxidation half reaction involves zinc solid becoming zinc 2+. But this is not quite balanced yet. We've balanced the atoms, but we still need to balance the charge. So I need to add 2 electrons, but where do those 2 electrons go? On the reactant side or the product side to make it all charge balanced? On the product side, yes, so plus 2 electrons. And remember, oxidation is loss of electrons, so the electrons should show up on the product side. And then we do the reduction reaction just the same, so we have copper 2+ becoming copper solid, and this time those 2 electrons go on the reactant side. I usually like to show half reactions this way, oxidation then reduction, because you can clearly see, oh, these 2 electrons that are products in the oxidation reaction funnel into the next reaction, the reduction reaction. Basically, the electrons given up in the oxidation go into the reduction reaction. And so we see this is the transfer of electrons that's occurring when we split up these half reactions. All right, so let's answer these questions. A little bit more detail about the reaction that's happening here. Okay, so how many electrons are transferred in this reaction? Well, it is 2. So we call this the N values, the number of moles of electrons involved in the transformation. And so here it is 2. Once you get those half reactions, it's definitely easier to see. What substance is losing electrons? So that would be zinc is what is losing electrons, because that's the definition of oxidation. But also remember, I had you memorize N-ox, red cat. So oxidation, this is the reaction that's happening at the anode, and for reduction, this is the reaction that's happening at the cathode. And so then we can answer the next question, what substance is gaining those electrons? So that would definitely be copper 2 plus in this case. Copper 2 plus is what's gaining those electrons to become copper solid, and that's at the cathode. So remember, N, ox, red, cat, if you ever forget. So if I say anode, then that involves the oxidation redox reaction. If I say cathode, that involves the reduction redox reaction. All right, and so then based upon these half reactions, or based upon what we see, which direction do electrons travel in this cell? So looking at these half reactions, you see, oh, electrons are produced at the anode and then consumed in the cathode. So they go from anode to cathode. All right, and then what metal is the anode and what metal is the cathode? Well, that's based on the half reactions that we identified. So oxidation is the anode, so the material there is going to be zinc solid, and the metal that's going to act as our cathode is copper solid. Perfect. So this is what the voltaic cell looks like. So we just, looked at all of the details of a spontaneous redox reaction, but we can set up a voltaic cell to harness the electron transfer event. Basically, you harness the electricity that is generated here by setting up a voltaic cell. So simply, we have two containers. One contains the anode, one contains the cathode. That contains the components of that redox half reaction. So here you see zinc solid. That is the anode. It's literally a piece of zinc in a bath of zinc 2 plus solution. So this is probably like zinc chloride or zinc nitrate to make it the ionic version. And then on the other side, we have the cathode, where the electrode is a piece of copper. And again, swimming in a bath of copper 2 plus, so probably copper nitrate. So these two solutions, they are connected by a porous salt bridge that allows ions to transfer from one side to another to remain charge balanced. But what's most important here is that we connect that electrode, the anode, to the cathode. And we can put either a voltmeter or some type of device here to use the electrons that are being transferred from the anode to the cathode. Because remember, we said, which direction do electrons travel? Anode to cathode. So if you put some type of device here, you can use those electrons before they spontaneously go from the anode to cathode. And that's essentially how batteries work, is we utilize these spontaneous redox reactions and the movement, the spontaneous movement of those electrons before they go to their destination. All right, so let's look into more details of this voltaic cell. Okay, so remember, a reaction is happening. Yes, electrons are going from your anode to your cathode, but a reaction's happening. We've talked about reactions. We can do the stoichiometry, right? Reactants to products, do a BCA table or whatever. So as this reaction proceeds forward, yes, electrons are moving, but what else changes about the components of this reaction? How do you think the mass of zinc will change? Just use your chemical intuition. Look at this chemical reaction. Tell me, as this reaction moves forward, what are we consuming? Reactants, and we're producing products. So how will the mass of zinc solid change as this reaction moves forward? Will it go up or down? It's going to go down, yes, because it's a reactant, right? And then how will copper mass, the solid, change? It's going to increase because it's a product, right? In that same vein, how do you think the copper 2 plus concentration will change? It's going to go down, yep, because it's a reactant, and then zinc 2 plus concentration will increase. You can think, oh, that mass of zinc solid that we're losing, it's going towards making zinc 2 plus, so it's going to increase the concentration. The mass of this anode is going to decrease, and then the concentration inside this water bath is going to increase. While on the other side, the copper electrode is going to increase its mass, while the ions inside that solution are going to decrease because they're depositing themselves on that copper rod. And you will do this in the VOL lab, though I think that lab is digital. So it kind of loses its awe, but that's something that you will explore, is how the cathode and anode gain or lose mass based upon how long you run a redox reaction for. All right, and so I mentioned before that, yes, when electrons move from left to right, you can think, oh, negative charge is moving from left to right. We are making more cations on one side. The copper 2+ concentration decreases while the zinc 2+ concentration increases. So what also happens as electrons move from left to right, as this reaction moves forward, is we generate positive charge on a certain part of this voltaic cell. So in order to maintain charge balance, we have to connect these two parts of our voltaic cell by a porous salt bridge that allows ions to transfer from side to side, and so each side stays charge balanced. So essentially this salt bridge acts as your completing your circuit, essentially, because electrons are moving from left to right, but we got to complete the circuit, so we connect those two halves with that salt bridge to complete that circuit. All right, and so the question here is, why do anions travel towards the anode? So I like to think about it this way. The anode is the oxidation reaction. So zinc is becoming zinc 2+, and so at the anode, zinc 2+ concentration is increasing. So you're increasing your positive charge on that side. So the overall positive charge increases. So to cancel that out, anions will travel towards the anode. Anions towards the anode, because you're basically accumulating positive charge because you're making more zinc 2+. Versus why do cations travel towards the cathode? Kind of for the same reason. If you look at the reduction reaction, which happens at the cathode, you can think, oh, copper 2+ concentration is decreasing. So you're losing, I guess you're losing positive charge. So that's why cations will go towards the cathode to basically replace all of that positive charge that you're losing on that side. All right, so you can kind of think your way through which way the anions and cations travel through that salt bridge, or you can just remember anions travel towards the anode, cations travel towards the cathode via that salt bridge. So the letters can help you memorize that. But you can think your way through it based upon how charge is accumulating. All right, okay, so those are the details of a voltaic cell. So now let's talk numbers. How can we predict a redox reaction happens not using the activity series table? So I mentioned that we are going to associate numbers with the qualitative concept that we learned about earlier. Now let's talk about numbers. A lot of these half reactions you can find in a standard reduction potential table. So in the textbook you have these tables where it's a bunch of different half reactions written in the reduction form, and there's a bunch of numbers written here. So these reduction potentials are measured at standard conditions because we got to reference it to something, make all of these reactions similar. So do keep that in mind, that they're at standard conditions. We will look at non-standard conditions a little bit later, probably on Thursday. But for now, when you use these table values, know that they are taken at standard conditions, and they are all referenced to the standard hydrogen electrode. So in order to get numbers, we need to reference ourselves to something. So we reference ourselves to the hydrogen, H+ hydrogen gas reduction reaction. So you can see that right here. All right, so our 0 point, we define it as the reduction potential of H+, so acid, gaining 2 electrons to make H2 gas. You can also remember from our activity series table, H+ was kind of in the middle of the table, and we kind of looked, okay, things above it can dissolve in acid, things below it can't dissolve in acid. So same idea here, we're going to reference ourselves to the hydrogen electrode. And so how they measure the potential for the standard hydrogen electrode, you can think this half reaction involves acid and it involves gas. So this standard hydrogen electrode is quite complex. So basically what happens in this electrode, you can purchase an electrode and hook it up to your voltmeter, is that they have the electrode submerged in 1 molarity acid. So if you calculate the pH of that, that's pH of 0, so that's fairly acidic. And so in that electrode is very concentrated acid, where that substance is going to be gaining the 2 electrons, but what's produced is hydrogen gas. So what you saw in this example with our electrodes, see how zinc was our electrode? It was our anode. Copper metal was our cathode, was also an electrode. Those things are solid, so they can act as electrodes. But can a gas act as an electrode? Can you put an alligator clip on a gas? No. You can put an alligator clip on a piece of metal, like a solid, but you can't put it on a gas. So to get around it, we actually have to use platinum solid to facilitate that electron transfer, where basically acid migrates towards the platinum, the electron transfer happens, and then the gas is generated and goes away from the platinum electrode. So the platinum is just kind of a surface for the reaction to occur. That we can stick an alligator clip on, because we can't do that directly to the gas itself, because this reaction does not involve any solids. So what you see from this standard hydrogen electrode is that it's quite complex. There's concentrated acid, we got to get platinum. So that's why we reference everything to this electrode. We had one person needs to do it once, measure the voltage that comes out for any of these other half reactions, and then we can always reference ourselves to it. So we don't actually have to use a standard hydrogen electrode all the time, and that's good because this is a quite complex reference electrode. So know that all of these values are referenced to that hydrogen, the standard hydrogen electrode, though you don't actually have to do it yourself, all right? So everything is referenced to that. Okay, so how can we read these numbers? All right, so I remind you that the activity series table primed you for reading tables like this, where we saw the hydrogen redox reaction or reduction reaction, and we saw that, metals above hydrogen were would typically dissolve in acid versus the metals below it would not. And the reason is, one, it didn't follow the rule of the metal being higher on the activity series than the cation, but really it's because when we combine these redox reactions in such a way, spontaneous redox reactions will always have a positive E cell, total cell potential. So when I say cell, I mean both the reduction and the oxidation reaction happening at the same time. Sometimes I reference half reactions, which I'm only talking about half of that cell, but for this slide, we are looking at, okay, what is the oxidation reaction, what is the reduction reaction? When we add those two half reactions up, do we get a total cell potential that is positive? And that is a spontaneous reaction. That is when a redox reaction occurs. So when we read this table, again, reference yourself to that 0 point. Okay, so our standard hydrogen electrode is right here, it's at 0. So all of these substances with positive reduction potentials, notice how all of these reactions are written in the reduction form. So all of these positive reduction potentials, all of these substances basically are reduced fairly easily. You can think, okay, the reduction reaction is a somewhat spontaneous reaction because it's more positive than the standard hydrogen electrode. These metals are usually the cathode because reduction is favored. Reduction is favored because they have higher, more positive reduction values. Versus the substance below hydrogen, standard hydrogen electrode, notice how these reduction potentials are negative. So these reactions are not very spontaneous in the forward direction as written. That these reactions don't really want to do the reduction reaction because they have negative reduction potentials. But if you flip a redox reaction, kind of like Hess's law a little bit, if you flip this, like for example, this nickel reaction, if you flip this reduction nickel reaction, it then becomes an oxidation reaction. So instead, you can think, oh, for these substances down here that reduction is not very favored, oxidation is favored instead. The reverse of the reaction is favored instead for these metals that are below hydrogen in this table. So you can think, okay, these substances with negative reduction potentials, they are typically oxidized relative to the standard hydrogen electrode. These metals are usually the anode. And again, you can think a fairly negative reduction potential means a positive oxidation reaction because it's the reverse of it. So yeah, we'll see that mainly these elements or these half reactions with positive reduction potentials are typically the the cathode, while these ones are typically the anode. Where oxidation occurs, we flip that reaction. So the equation that we're going to use all the time is this one. That the cell potential, the overall cell potential, the overall redox reaction voltage is the reduction potential that happens at the cathode minus the reduction potential of the reaction that happens at the anode. Notice that there's a minus sign and both of these numbers are in the reduction form. So I'll point out that if, let's say, we did a redox reaction between like permanganate and nickel or something, and we said that, okay, this is the cathode, this is the anode. To calculate the cell potential, we would take the cathode number from this table and just subtract the reduction potential that happens at the anode. So we just subtract these numbers as written. All right, and so that subtraction is what does the flipping of the anode reaction for you. So you don't need to flip it twice. Don't change this sign and subtract it because then you undo the negative sign that you just did. So just follow this equation exactly. Keep both numbers in the reduction form because that's usually how they're presented in the table, but just locate what is your cathode, what is your anode, and do cathode minus anode, both of those values in the reduction form. You'll probably make the mistake here in a little bit, but hopefully you'll do enough practice with me that you'll see the strategy. All right, so let's keep going. Okay, so let's use this reaction in some experiments. So let's explore some experimental data and determine, let's use this experimental data that's presented and determine what are the reduction potentials of copper 2+, zinc 2+, and H+ in voltage. So we're going to basically confirm the numbers that are up here, all right? So here are the experiments. So it looks like we set up a voltaic cell between zinc and H+, and it reads this cell potential. So this is E cell. Right here, this is our voltmeter. Here is E cell for these two reactions. So we want to determine what are the cell potentials of these substances given the observations of the overall cell potentials. We want the reduction potential, sorry, of these substances. One of these half reactions we should know already, and that is the hydrogen half reaction reduction potential. What is the voltage for the hydrogen, standard hydrogen electrode? That's a definition. What is it? It is 0, yes, because that is our reference point. So we know one of them already, and that's going to help us tremendously in the rest of these experiments. Because what we are going to use here is the equation that the cell potential is equal to the reduction potential of the cathode minus the anode. So if we simply look at these experiments, we'll do them one at a time, and locate which substance, which side is our anode, which side is our cathode, we'll be able to determine what that missing piece is. Typically for these voltage or these voltaic cells, they're always set up where the anode is on the left side and the cathode is on the right side. Because we always want electrons to go left to right because we read left to right, and so typically they're written anode to cathode where electrons move left to right. So just based upon where they are, we can locate, oh, okay, hydrogen is the cathode. We know that that has a 0 voltage. We are trying to figure out what is the reduction potential of the anode? So in this case, it's zinc. And both of these things have to add up to the overall cell potential. So that's given right here in the voltmeter, that E cell for this reaction is equal to 0.76 volts. And then we have to do cathode minus anode. We already know what the cathode is because we identified it as hydrogen. And so we can figure out what is that reduction potential for our anode. So I'll just go ahead and actually put values here. So 0 volts was our cathode. And we're going to subtract and calculate what is the reduction potential of our anode. And so simply if you move those things around, I think you get that the reduction potential of our anode in this case is 0.76 volts. So that's that missing piece. But we had to identify, okay, what half reaction's happening at the anode and then what is happening at the cathode. If you look at the previous slide, I think that is correct, that zinc is, where's zinc? Zinc is, oh wait, did I do the math wrong? Anode, cathode, oh yeah, I did do the math wrong, I'm sorry. It's negative 0.76. Yes, I had to subtract that number from 0, negative 0.76 volts. Sorry about that. So I just moved this guy to this side and then subtracted 0.76 from 0, but I forgot about that negative sign, so there it is. All right, so zinc has a reduction potential of negative 0.76, and that matches exactly what was given in this table. Zinc, because of its negative reduction potential, is typically the anode, and that's exactly what we see in this diagram. So let's use this information to help us with experiment 2. So here we have a different composition of our anode and our cathode. This time it's zinc and copper. So again, anode is on the left side, cathode is on the right side. We actually already know the reduction potential of our anode of zinc. In this case, it's negative 0.76 volts. We already got that from experiment 1. When we put together all of the information, that the cell potential in this case is equal to 1.10 volts equals cathode minus anode. This time we are calculating what is the cell potential of the cathode, that missing piece. So in this case it's copper, and so that's what we're calculating, the reduction potential of our copper cathode minus the anode value we got from experiment 1, so minus negative 0.76 volts. And so I think we see that the reduction potential of that copper cathode, okay, so E cell equals, 0.34 volts. So that's the missing piece there for our copper half reaction. All right, so this is us utilizing this equation, cathode minus anode. Both of these values are all reduction values. So if you compare these two things, all of these answers, they match exactly what's up on this table. If you locate where hydrogen is, nickel is, and copper, yes, those answers do in fact match. And so if we think about the last question here, if we set up a cell where copper and hydrogen were mixed together, all right, in a voltaic cell, what would be the cathode? So remember, if this is a voltaic cell, we need a positive cell potential. So if we look at our answers that we just got, the reduction potential for copper is 0.34 volts, while hydrogen is 0. So you need to think to yourself, how can we combine these two substances? Which one has to be the cathode? Which one has to be the anode for a positive number to come out? And so we're subtracting these two numbers. So in my mind, if I take 0.34 minus 0, a positive number comes out. So in this case, copper will be the cathode in this case. Because that's the only combination that a positive cell potential comes out. If it's the other way, if I made copper the anode, it would be 0 minus positive 0.34, and a negative value comes out. That would not be a spontaneous reaction. So copper has to be the cathode in that case. Okay, so let's, I didn't know when to do this demo, so let's do this demo. All right, so in the second experiment, we combined zinc, a zinc half reaction, and a copper half reaction. So I have that voltaic cell up here, all right, where you can clearly see I have a copper strip and a zinc strip. Both of these things are swimming in a ionic solution of their cation. So this copper half cell is swimming in copper 2+, that's why it's blue, but the zinc solution is swimming in zinc 2+, which is just a colorless solution. So both of these solutions, these are both of the half reactions, the halves of the voltaic cell. They're just sitting in one another in a porous cup that's acting as our salt bridge to complete the circuit. So right now, the circuit is not completed because these two electrodes are not connected to one another. So the circuit's not completed. A redox reaction is not happening until I connect these two electrodes. So let's just prove that when I put in contact a zinc half reaction and a copper half reaction, that a reaction does in fact happen. So right now I have a multimeter. Okay, I don't know if you probably can't see this, but you can try. All right, a multimeter, and right now it's reading 0 because nothing is connected to it. But if I complete the circuit while connecting my voltmeter, basically replicating this picture of the copper half reaction and the zinc half reaction, what cell potential do you think I'll measure? Well, if we look up the cell potentials of copper and zinc, you can see up in here, where's my pen? So what's happening is I'm combining the copper half reaction and the zinc half reaction. So if you look at these two highlighted values, think to yourself, how can I combine these in such a way that a positive number comes out? Well, if copper is the cathode and zinc is the anode, then a positive number will come out. What positive number comes out? 1.1. So let's see what happens. So right now this measures 0, but then if I connect these two things, a cell potential of, can someone read that? It says 1.06. So really close to 1.1, all right, once I connected the circuit. All right, so I identified the cathode and the anode, but here's the thing. Electrons are stupid. What if I swap the cathode and the anode? All right, so what I'm going to do is just swap the electrodes. Actually, I forgot which way I did it. If I swap the electrodes, you might think, oh, if you swap the cathode and the anode, a negative cell potential comes out, and that's not spontaneous. But the thing is, electrons are stupid, and the electrons will always move in such a way that's spontaneous. And so they're just going to go through the voltmeter the opposite way. So instead of reading a positive 1.1 voltage, you'll just read a negative 1.1 voltage. But that just has to do with polarity. Which way are the electrons moving in here? All right, so the voltmeter shows the cell potential that's generated. Basically what it's measuring is the electrons moving from one side of the cell goes through the voltmeter to the other side of the cell. But I mentioned in this chapter, we're also going, not just, a spontaneous reaction doesn't just happen. We can harness the movement of electrons to do work for us. This is how batteries work. So here I have a little DC fan that instead of connecting this cell to a voltmeter and measuring the voltage, let's actually make those electrons do some work. So let's see, I'm going to connect the two electrodes there to the anode, here to the cathode, and we'll see what happens. There we go. All right, so instead of the electrons moving through the voltmeter, I'm making it do work, in this case spinning the little fan. All right, so here the electrons are moving from the anode to the cathode to make this little fan run. What if I swapped the identity of the cathode and anode? What do you think would happen? Is it still going to spin? It will still spin, but what's different about it? It's just going to spin in the opposite direction. Even if I swap out the cathode and the anode, the electrons are just going to move, again, from anode to cathode, but it's just going to spin the other way, right? So there's certain safe gaps in our electronics, like polarity protectors that prevent electrons from traveling in the wrong direction in your electronic device, but this thing is just very crude and archaic, so there's no such polarity protection in here. There's like certain fuses in your cars because they are hooked up to batteries to prevent polarity switching. But yeah, this can go on for a long time. We'll see how long this will go for the duration of the class. So hopefully that's not too distracting. All right. So we're harnessing those electrons that are moving from the anode to the cathode there. Okay. So how else can we represent reactions? So notice that, where do I want us to say? In a balanced redox reaction, usually this is how we depict reactions, right? Zinc solid reacts with copper 2 plus to give zinc 2 plus copper solid. So here we've organized the substances just based on reactants and products. But if you look at a voltaic cell, that's not really how it's depicted. In a voltaic cell, we put all of the anode stuff in one compartment. In the other compartment, we put all of the cathode reduction stuff. So we can use line notation to help represent what's happening in a voltaic cell a little bit more clearly. So line notation tells you exactly what's in your anode and exactly what's in your cathode, but it does not necessarily tell you what redox reaction is happening. So that's up to you to interpret, as long as you know what's happening in the anode and what's happening in the cathode. So this is just an easier way to show what a voltaic cell is set up, because to be honest, to draw this in like a Word document is very difficult, but what is not as difficult is writing line notation like this to tell you exactly what is in your anode compartment and what is in your cathode compartment. So to read this, here I showed you, here's the zinc copper voltaic cell, so exactly what we have down there. This is hard to draw in Word, but instead we can represent it in saying, okay, these substances are what's in your anode, your oxidation half reaction in your anode compartment, and everything on the other side of this double line salt bridge boundary is everything in your cathode compartment. So typically how we write line notation is say exactly how electrons are being transferred. We put a single line to mean a phase boundary. So if you look here, we have zinc solid, that is our anode electrode. We put a phase boundary to mean that zinc is in contact with zinc 2 plus. That's also present in your anode compartment. And then to separate to your cathode compartment, we put a double line. This double line is what means salt bridge. We're connecting our cathode to our anode, and then you kind of do it backwards. You put copper 2 plus, that is the solution that's in contact with your electrode, in this case copper. And so this type of writing is a lot easier to show, okay, these are the things that are happening in your anode, these are the things that are involved in your cathode. And you can see exactly what components are required there. And remember, the anode involves your oxidation half reaction, and your cathode involves your reduction half reaction. So when we draw it this way, we kind of lose that sense of what's happening, but it's easier and better represents what our voltaic cell actually looks like. So let's practice that with writing the line notation for this reaction. All right, so this is the setup. You want to say, where are your electrons starting in your anode, and then how is it going to your cathode? So in this case, instead of zinc solid being our electrode, here we have magnesium coil. So in this case, it's magnesium solid. This is where we're starting. All right? Magnesium solid is in contact, so I'm going to put a single line to mean phase boundary, is in contact with a solution of magnesium chloride. So in this case, magnesium is in contact with Mg2+, so aqueous. If these things had a concentration, this is where you would put it. So if we're talking about standard conditions, this is 1 molarity of magnesium 2+. Right? So that's everything that's in our anode compartment. So let's be electrons and go through our wire, our voltmeter, and go to the cathode compartment. So to separate those two compartments, do a big double phase boundary, double line. And now we describe everything that's in the cathode compartment. So this is in a solution of HCl. So this is H plus aqueous. And let's just say it's 1 molarity because we're at standard conditions. So 0, pH 0. But what is acting as our electrode here? Platinum, yeah, so instead of like magnesium or zinc or copper acting as our electrode here, you can see that that little piece of metal here is actually a non-reactive platinum wire. So in this case, it's platinum, solid. But I'm missing one last piece. So we have a solution of HCl, but there's also bubbles of H2 being produced. So this is our standard hydrogen electrode that we mentioned before. So I also have to show that hydrogen gas is being generated here, so I want to put H2 gas as well. All right, and more phase boundaries in there because gas is a different phase than things that are aqueous. So that is what our standard hydrogen electrode in contact with a magnesium half reaction would look like. You've done this in lab. You've put a strip of magnesium into acid, generated H2+, but here we can set it up as a voltaic cell and actually harness the electrons that are being transferred in this event. So notice I just put everything that's in the anode here. I put everything that's in the cathode compartment over here, separate substances by phase boundaries. If things are in the same phase, then you don't need that phase boundary line, but everything is sandwiched between the two electrodes. So in this case, our anode electrode is magnesium, and for our cathode, it has to be platinum because you can't put an alligator clip on a gas, but you use a metal instead. So when gases are involved, typically platinum is our electrode. All right, so that is line notation. So let's use the cathode minus anode equation a little bit more here. All right, so a voltaic cell is based upon these two half reactions. So remember, voltaic cell means spontaneous reaction. So we want to get a positive cell potential out. That's our goal. Because right now, I just tell you what the half reactions are. I don't tell you what the anode is. I don't tell you what the cathode is, but you can figure it out. Because voltaic cell means positive cell potential. So use this equation, cell potential equals cathode minus anode, and use these cell potentials and ask yourself in which combination, what's the cathode, what's the anode, what combination gives us a positive cell potential. There's only one combination. Which of these two substances, this tin or the cadmium, is going to be our cathode? Tin or cadmium? It's going to be tin, yeah. So this one's going to be our cathode. And then the cadmium one is going to be our anode. If you have no idea how I did that, there's only two possibilities. Just subtract them from one another, and only one of those combinations, a positive number, is going to come out. So when you do it this way, tin minus cadmium, you'll get a positive number comes out. In this way, you get negative 0.14 minus negative 0.40. A positive number comes out. But if you did it the other way, where you said, oh, cadmium's the cathode, tin is the anode, in that case, it would be negative 0.4 minus negative 0.14, and a negative number would come out there. All right, so it's not the other way. Tin has to be the cathode, cadmium has to be the anode. All right, so yeah, in this case, tin is the cathode. All right, so let's just go ahead and calculate this, but I want to show you the half reaction that's the redox reaction that's actually happening. So here it's, cathode minus anode. We determine that the cathode is tin, the anode is going to be cadmium, and so this is going to be negative 0.14 volts minus negative 0.40 volts. And so the value you get out here is that this cell potential is going to be around 0.26 volts. All right. Oh, and write the line notation for this cell. Yes. Okay, so here we have the cell potential. So we just did the math, calculating what's the anode, what's the cathode. So at the anode, that's the cadmium reaction. So remember, at the anode is what oxidation is what occurs. But these two reactions that are given are in the reduction form. So we actually have to flip this reaction, the cadmium reaction, because that's what's happening. That cadmium solid is being oxidized to cadmium 2+, and you're giving off 2 electrons. That's the reaction that's happening at the anode. While at the cathode, this cathode is where reduction happens, so we can just simply rewrite the reduction reaction. Tin 2+ is gaining those 2 electrons, and you're making tin solid. All right. So those are the reactions that are happening at your anode and your cathode. So now we can put that line notation together. You can write the line notation showing, okay, electrons are traveling from your anode to your cathode, where you want to sandwich your 2 metals on the very ends. So if we write anode first, it's going to be cadmium solid in contact with cadmium 2+ aqueous. So it's probably going to be 1 molarity, again, because this is standard conditions. Phase boundary to show, okay, the anode is in contact with your cathode. So here you're going to write tin 2+ aqueous. That's in your cathode compartment. And then that is in contact with a piece of tin. So tin solid. So notice that we have the metals on the outside and everything in solution on the inside connected by that salt bridge. But what actually generates the voltage is connecting cadmium solid to your tin and then like putting a voltmeter here. All right, where you connect those 2 electrodes to one another. And that's how we complete that circuit. All right, so there is the half reactions, the calculations, and the line notation. So let's do one more. Another one. All right, so these half reactions, so here I give you 3 of them. We're going to use the same equation. Overall cell is cathode minus anode, everything in the reduction form. Which combination produces a reaction with the largest EMF? So EMF stands for electromotive force, which is the same thing as cell potential. So you can just think EMF means E cell. That's what we're calculating. We want the most positive E cell that comes out. We have 3 different substances. So you can ask yourself, okay, which substance is most likely to be the cathode? If you just think about this mathematically, if I want a positive cell potential to come out, if your cathode is a very positive number and your anode is a very negative number, that's how you can get the most positive cell come out. Or you can think, okay, your cathode is something that's highly reduced versus your anode is something that's highly oxidized, so you're going to want to look for a negative value. So in this case, the third reaction is what is our cathode is going to be. That's how we can get the most positive cell potential out. So then which substance is most likely to be our anode, the first one or the second one? The first one, yeah, this one is going to be our anode, because it's the most negative reduction potential, meaning that it's a really crappy thing at being reduced, but it's really good at being oxidized. So it would rather be a anode. All right, so yeah, we want to do reactions 1 and 3. Those are what's going to be our largest EMF here. So if we calculate the cell, E cell for this, it's going to be the cathode value, so 0.49 volts, minus the anode value, so negative 0.86. Again, notice that I'm just using the reduction values as is. That minus sign is what's doing the flipping for me. So again, don't do it twice. And then add those 2 numbers up, and yeah, you get a fairly high cell potential of 1.35 volts if you combine those 2 things. The, what is that, a gold bromides solution, half reaction, and an iodide half reaction. So let's write the overall balanced reactions for these cells. All right, so just like before, but here I already have the half reactions for you, but both of these are in the reduction form. So you want to take that anode reaction and recognize, oh, this is my oxidation reaction. So that reaction as written isn't what's happening. These are in the reduction form. So in order to make an oxidation reaction, I have to flip it. So the oxidation reaction is actually flipped. So really what's happening is silver solid is combining with 4 bromides to give silver bromide and 3 electrons. That's my oxidation reaction. While my reduction reaction, this is what's happening at my cathode. We can just copy exactly as written because it's already written in the oxidation form. So IO minus plus H2O plus 2 electrons give us I minus plus 2 hydroxides. So these are the 2 half reactions. Can I add them up just as is right now? So remember how we balanced redox reactions? In order to add up 2 half reactions, what have to match? The number of electrons. So before we add them up, we just need to multiply by a coefficient. So notice that this reaction releases 3 electrons, this one consumes 3 electrons, so I'm going to multiply by 2 and 3 in order to add these reactions up. So, and then that gives me 6 electrons for being transferred in this event. So the total balanced reaction is 2 golds plus 8 bromides plus 3 IO minuses plus 3 waters give us 2 gold bromide complexes plus 3 I minuses plus 6 hydroxides. All right, so in green I have the balanced reaction. So here I already gave you the half reactions and we just had to add them up to make sure that the electrons canceled out and that we correctly identified what was being reduced and what was being oxidized. So a little bit easier than actually balancing each of those half reactions as is. So if you look at the balanced reaction that we got, before, when we did balancing like the full long way, we always balanced in acidic conditions. But this balanced reaction is actually in basic conditions. How do I know that green reaction is in basic conditions? There is hydroxide present. So let's convert this reaction that's in basic conditions to acidic conditions. So let's convert it back. How do you think we can convert the basic conditions back into acidic conditions? Think about how we did it the other way. How did we convert acidic to basic? We added and neutralized the H plus using hydroxide. But in this case, because we already have hydroxide, what I want to do is actually add 6 H pluses to each side to balance it back into acidic conditions. Because these 6 hydroxides and 6 H pluses actually become 6 waters instead. All right, so those 6 waters will cancel out with some of the waters that are already present in this reaction. So those 3 waters cancel, and then this becomes a 3. So the full balanced overall reaction in acidic conditions is 6 H pluses, 2 golds, 8 bromides, 3 IO minuses, 2 of the gold bromide complexes, and 3 I minuses and 3 waters. So that's the reaction in acidic conditions. This would have a different cell potential, but that's not part of the question. I just wanted you to convert between basic and acidic conditions one last time. All right, so are we going to do another one? Yes, okay, so let's do another one. Okay, given these 2 cell potentials, all right, so this is kind of similar to the previous question where I had 2 pictures of different experiments and you had to determine what was the reduction potential of the missing pieces. This is the same thing, except they're just not pictures. I just give you numbers instead. So I'm telling you, okay, copper has a reduction potential of that. You can look that up. And I tell you, in this first cell, you connect copper with nickel, and you get this cell potential come out. Like you connect these 2, the anode and the cathode, you hook up your voltmeter, and this is what you measure, a cell potential of 0.62. Then you connect nickel with some unknown substance, and you get a different cell potential come out. So tell me, what is the reduction potential of this missing piece in cell 2? So this is similar to what we did before. we need to identify ourselves what is the cathode, what is the anode, because in this question we are going to utilize the equation E cell equals the reduction potential of your cathode minus the reduction potential of your anode. So we need to figure out what is the cathode, what is the anode for all of these things, and do the subtraction carefully to make sure that we can calculate the reduction potential of that missing piece. So simply, my strategy is, okay, figure out what is your cathode and what is your anode in each of these reduction potentials, and then do the subtraction with those given numbers. So in this case, nickel is going from 0 to +2, so it is being oxidized, therefore it is the anode in this reaction. Okay, I don't know how to spell. Anode, great. Copper, on the other hand, it's going from +2 to 0, so it is being reduced, it is the cathode. All right, so when we put together this equation, E cell equals cathode minus anode, I'm given cell potential. I'm given the cell potential of, or sorry, the reduction potential of the cathode. In this case, copper was already given. So I'm going to calculate what is the cell potential, or the reduction potential of the anode, that missing piece. In that case, it's nickel. So in this case, putting the numbers together, 0.62 volts, that is what was measured. We know the reduction potential of our copper electrode, but we're calculating the reduction potential of the nickel electrode. So in this case, it's 0.34 minus the reduction potential of that nickel, that missing piece. And so if you calculate that, I think, let's see, 0.34 minus 0.62, we get that the reduction potential of nickel, that missing piece, is negative 0.28 volts. Do you see how I got that? It's all about locating what is the cathode, what is the anode, and then recognizing you're plugging in the reduction potentials of both of those, and they have to subtract to the given measured cell potential of the overall redox reaction. All right, so that is the reduction potential of nickel. Hopefully, if you look at the table values, it matches. And we're going to use that in the second equation, because in this equation, let's look and see what's happening. Nickel is still being oxidized. It's going from 0 to +2, so it is still the anode here. But this time, we have some unknown substance being reduced. It is the cathode. And overall, it gives this different cell potential. So the idea here is we're going to use the exact same equation, E cell equals cathode minus anode. But in this time, we know the cell, we're solving for the cathode. This time we know what the anode is. All right, so plugging in those numbers, 0.52 equals the reduction potential of the cathode. In this case, it's X, like whatever this unknown substance is, minus the reduction potential of the anode that we got in the first part, so negative 0.28 volts, all right? And so we see, yes, that this missing piece, that the reduction potential of that missing piece is something like 0.24 volts. That is how we can get everything to match the experimental measured cell potential using that voltmeter given those missing pieces of the two different cells. That nickel was used in two different places, so we were able to forecast that on the second cell to figure out what that missing piece is. So again, we are just using this equation. Cell potential is equal to cathode minus anode, both of them in the reduction form. All right, so how else can we read reduction half reactions? So I'll remind you that our goal is to have spontaneous reactions, is we want this cell potential to be very positive, right? In order for the cell potential to become positive, if the cathode, the thing that is being reduced, has a very positive reduction potential. More likely, a positive cell potential will come out. Or you can think if the anode is very, very negative, the reduction potential for the anode is very negative. Remember, this is where oxidation occurs. That's another way you can get a really positive cell potential. This all has to do with reducing or oxidizing power of your different substances based upon this table. So here's just a couple substances. Here are a couple reduction values. All right, so here are your reduction values for these different reduction half reactions. So silver, copper, H+, lead, and zinc. So based upon these numbers, tell me, which substance is the best oxidizing agent? So think about what this question's actually asking. So I have a bunch of stuff on here. So obviously you're going to pick one of these things. One of these things is the best oxidizing agent. So remember how we balanced half reactions? Oxidizing agents are what in your reaction? What happens to oxidizing agents in a reaction? They are actually reduced, yes. So really, if this question is asking what is the best oxidizing agent, it's asking what thing is the best thing that is reduced. So remember, oxidizing agents are reduced. So remember, all of these half reactions are reduction half reactions. So which substance is the most easily thing reduced? You're looking for the most positive cell potential. So in this case, it's silver plus. Right? You're looking for the most positive reduction potential, the most positive one. Because the most positive reduction potential has the most favorable forward reduction reaction. Right? So silver in this case is the most easily reduced because its reduction potential is the highest number. On the other hand, which species is the weakest oxidizing agent? In this case, it's going to be zinc 2+. Because it has the smallest, it has the most negative reduction potential. It doesn't want to go in this direction. Zinc 2+ doesn't want to go to zinc 0 because it has a negative reduction potential. This is not favorable, right? So in this case, the strongest oxidizing agent is the thing that is most easily reduced. In this case, you're looking for the most positive reduction potential. Okay. So I mentioned here, all right, so this reaction, zinc 2+ to zinc 0, is not spontaneous. Zinc does not want to be reduced. It's a negative value. But if we flip that reaction, if zinc solid becomes zinc 2+, now the oxidation half reaction has a positive voltage. This is spontaneous. So kind of like, you know, stronger the acid, weaker the conjugate base. Similar in that the crappier the oxidizing agent, usually the better the reducing agent. And that's what we see here. All right. So in this case, zinc 2+, really crappy oxidizing agent. But if we flip the reaction, zinc is a really great reducing agent. Reducing agent. All right, so if we ask the same question here, what substance is the strongest reducing agent? Remember, reducing agents are things that are oxidized. So if you look at this list, the things that aren't very good at being reduced are actually really good at being oxidized. So in this case, zinc 0 is the best reducing agent. Because remember, the oxidizing reactions are the reverse of these reactions. So zinc 2+ can't be further oxidized, but zinc solid can. So here we're pointing at the products of these reduction half reactions versus the species that's the weakest reducing agent here would be silver solid. Because again, all these things are being oxidized. It has the most positive cell voltage of, the most positive reduction potential, so it's going to have the most negative oxidation potential. So silver solid is going to be the weakest reducing agent here. It's not likely for it to be further oxidized because it's not very spontaneous to do so. So you're looking for the most I guess, negative reduction potential, because what that means is that the oxidation potential is really high, since those are just reverses of one another. Here, the weakest reducing agent will have the highest reduction potential, meaning that it has the lowest oxidation potential. Okay. All right, so that's kind of just conceptually how we read this table. Remember that a reduction reaction is just the reverse of an oxidation reaction. And I think that's where the trickiness of this chapter comes into play, because whenever you look at table values, they're always written in the reduction form. But if you want oxidation reactions, you don't have to go to a new table. You use the same table, but recognize it's the same table, but in reverse. All right, so we'll get to, we'll do this slide. And is that a good place? That might be a good place to stop. Yeah, probably. All right, so let's use this table a little bit further and see if we can't conceptually determine with these numbers, H plus can oxidize which of these species. So it's all about reading comprehension, because oxidize and reduce, they're opposites of one another. So if H plus is being the oxidizing agent, that means H plus is being reduced in our reaction. So if we're using this same E cell equals cathode minus anode to calculate whether the reaction is spontaneous or not, that means H plus is our cathode, and these different substances are going to be our anode. And so you need to ask yourselves, if H plus is right there on our table, which substances will react with H plus? Which substances will H plus act as the cathode and the other thing act as the anode? So if you look at this table, it's all of the things below. Oh, wait, sorry. No. Yeah, it's all of the things below. H plus will react and make a positive cell potential come out. So in this list, lead is the only thing that will react with H plus. Notice that you can't combine H plus and lead 2 plus. Those are both cations. One thing has to be oxidized, one thing has to be reduced. So in this case, these things are oxidized. You want to think, can these things be further oxidized? Copper 2 plus and lead 2 plus can't be further oxidized, but the solid metals can. Because remember, the oxidation reactions are the backwards of these reduction half reactions. So similar thing, zinc 2 plus can oxidize which species? So it's the same idea, but this time, zinc 2 plus is being reduced. All right, so these things are being, or zinc is being reduced, while these things are being oxidized. Or you can think zinc 2 plus is our cathode. One of these things is our anode. All right, so we know that the cathode is zinc 2 plus, so this is going to be negative 0.763. So you can ask yourselves, which one of these substances can we add, or sorry, subtract as our anode to get a positive number come out? And so our options are silver and lead. Oh, wait, hold on. I think silver will work, right? Silver will work? Because if we do negative 0.763 minus, oh wait, no, that won't work. No, so wait, zinc 2 plus is the cathode minus 0.7, nope, never mind, that won't work. Will just become more negative. No, so none of these numbers we can subtract from negative 0.76 to get a more positive number come out. So none of these will actually can be oxidized by zinc 2 plus, because none of them, E cell is never positive for any of these combinations, right? So if you look at silver and lead, where, let's see, lead is right here and here is silver. If you subtract those two numbers, we can never get a more positive number come out. All right. So let's do the same thing, but kind of backwards this time. So here zinc is doing the reducing. So zinc is the reducing agent, zinc solid. So that means it's kind of backwards thinking here. Zinc solid is being oxidized. And then we ask ourselves, which things can these be reduced by zinc solid? So kind of, again, backwards thinking, lead and silver, the solid form, can't be reduced any further, all right? So if zinc solid is being oxidized, now if you look at this reaction or this equation, now we know what the anode is, and we're asking ourselves, what are the possible cathodes we can get so a positive cell potential can come out? So zinc in this case is the anode. All right, so we are subtracting a negative 0.76 value. And so if you look at our possibilities, lead and silver, both of them, if these are the cathode, both of these will result in cell potentials that become positive, right? So it's all about language here. Here, zinc is doing the reducing, so it's being oxidized. So notice that that is the identity of your anode. And so we're asking, what is the identity of our cathode in this case? And so we're going to point to lead 2+ and silver+. But don't point to just lead and silver, because those are the solids. They cannot be further reduced. Those are the products of your reduction half reactions. And so in the last one here, can copper solid reduce which species? So same idea, but just different numbers. And this is definitely a tricky part of conceptualizing these reduction half reaction tables. So same idea, copper solid is doing the reducing. So it is being oxidized in your half reaction. So if copper is being oxidized, it is the identity of your anode. So if you circle this, copper is our anode, so we are going to subtract 0.337. So you ask yourselves, what is the identity of my cathode to give a positive number? And you see that the only combination is silver+, is the only one where if this one is the cathode and this one is the anode, then a positive cell potential comes out. All right, so there it is conceptually. We'll do a couple more of these and look at non-standard conditions on Thursday. I do anticipate that we will finish the first part of chapter 20, so do anticipate that that first homework set will be due on Monday. Stay safe and dry.